damped vibration systems. Derive the equations from the it is also called as single degree of freedom with damping. This is called as, suppose they will questions, they will give directly derive equations like this. Otherwise, they will give the equations for the given diagram. The diagram is this is the diagram. Once they will give the direct questions, or otherwise they will give the this one. This is the K is stiffness, C is coefficient of damping. We already know that one. In this system, the following forces are acting. Force due to the inertia, force due to damping, force due to spring, this already force due to the inertia, we already last derivation we used small m x power of double dash. It is called as acceleration. Another one is c coefficient of damping, x double naught, it is velocity. Another one is k into x, k into x is displacement. This already we know this one. In this system, what are the forces acting? Force due to the inertia, force due to the damping, force due to the spring. But free vibration means f of t is 0. We already know that one. Correct. The differential equations for the given solution is equations for given solution this is equation 1. What is mx? This is the force due to the acceleration. Force due to the damping is c into velocity. Another one is force due to the displacement. We can remember like this. Since f of t is 0, because free vibration, that is called as free vibration. Okay. Now, in this solution, we cannot solve the equation. So, we have to try a solution. Assume x equal to e lambda t. For solving this equation, we have to assume some constant. That I am assuming that one is x equal to e lambda t. That means partial derivation differentiate with respect to the t. Lambda e power lambda t. Understand? I am differentiate with respect to the t, then the value will be get. This value substitute in the equation 1. Lambda square e lambda 2 please plus c lambda e power lambda t plus k into e power lambda t equal to 0. What I am doing here, take the all the lambda. I am taking the common e power lambda t. Then the equations become n lambda square plus c lambda plus k. This is the equation 1 from the after the applying of value of x. The equations I rewrite as the lambda square or lambda and interchange that one. That equation 2. Here e lambda t is equal to 0. We understand that one. This equation 3 looks like a stochastic equation, quadratical equation. That it is looks like a characteristic equations. We can solve this equation. We can get how we solve quadratic equations. Formula is minus b plus or minus root of two a. We already know minus b plus or minus b square minus 4ac divided by 2a. We already know that. Here b is c. In this quadratic equation, again we have to problem for the m. So we commonly divided in equation 3. M divided by equation 3. Hence, lambda square plus lambda c by m k by m equal to 0 equation 4. Understand? In this quadratic equation, we already know that how to solve that. We have to apply this formula minus b plus or minus b square minus 4ac divided by 2a. Here, this is the b, this is c, this is a. I am applying that one. Minus b is c by m plus or minus root of b square means c square by m square 4. A is 1, here 1, hence 1 into c is k by m. Again common term is 2 by A. The equation, what I am doing there, B is, here B is C by M, A is equal to 1, C is equal to K by M. In this values I am applying, we can get the quadratic equation formula. We know quadratic equation, two roots is there. One is negative, one is positive. We will see that on how the lambda 1, 2. That is quadratic equation has the two roots, hence 1 and 2. Understand? This is called as equation 5. This equation is called as the in this C square by M square by it is called as radial or discriminant form. We understand the term. If we solve this, if we solve this value, we can get the quadratic equations or this radial or discriminant term in the three cases. One is positive, another one is negative or equal to 0. That is called as. So, based on the radial or discriminant term, we can classify it into three terms. One is discriminant function is positive, then it is called as overtime unit system. It is positive always. If discriminant function, this function is less than negative or less than 1, it is called as negative. Then it is called as underdamping or critical damping system. If positive means it is 3, we can classify into 3 categories. One is positive, it is positive. It is called as overdamping. Negative, underdamping system. Zero, it is equal to 0. It is critical. From the roads, we can assume the 3 categories. based on the roots. The discriminant term is positive greater than one. Sorry, greater than 0, then it is called as over system. In this, the roots are positive. The roots are positive, real, and the discriminant term is positive. It is positive or greater than 0. The over it is called as four-term system. But in this, characteristic equations are real and distinct. Similarly, if a discriminant term is negative, less than 0 is called as undertermed system. The characteristic equations in this characteristic equations are imaginary and negative. In this real, that is imaginary, and it is complex. Imaginary. If the discriminant is function is exactly 0, is equal to 0, then it is called as critical timing system. And based on the roots following cases already we discussed, in this again I have to reminder because the free vibration with damping has the three characteristics. One is over damping, under damping, another one is critical damping system. In this systems we can classify. How we can classify? Some definitions are required. So we have to assume the discriminant function is equal to 0, then it is called as critical damping. If it is negative, it is called as undertangling system. The roots are lies in the imaginary and complex manner, and a discrete time is positive, then the roots are lies in the or characteristics of the real and distinct functions. Understand? If we have solved these three equations, we get the solutions. First we will take this the critical damping system, because it is equal to 0, then easily we solve the equations. That equations for the critical damping. We will solve this one, we can get the solution. If square means that root will be gone. Here c square is equal to m square this is the, we can get the radial form. We already know that omega n square is equal to, if omega n is root of k by m. In a previous problem we already solved this one, so we will see one by one. If c square is equal to we will apply directly root, we can get the one type of solution, that is k by m is root of this one. Okay, so here we can put the omega n square, this one. Since this is the critical damping, so c by cc is critical damping, so 4 the solution is 4kn this one. So we can take the root, means we can take the root. Suppose we are taking root 4km and 4 2 then omega n. How it is omega n thing? Omega n square we already know k by m. If omega n means k by m, then it is the k by m is root of, we are taking common root, so root of k by m, it will become the omega n, m square will become the m. Here both sides are 2 omega n is equal to m is equal to 2 root of k by m. Hence, if you need omega n value, omega n is, we already know, natural frequency. Always for the all critical damping or over damping, natural frequency will be required. For the free vibration, forced vibration is the damping frequency they will ask. The three types of solutions came from the critical damping system. So from this one we can solve all this one. First one is Cc is equal to critical damping is 2 root of k by m. We are directly take the root. Another one is Cc by Cc 2 omega n1. Both sides we are taking the value. Then omega n value is the 2 root of km by 2m. This is also one type of solution. We find out from the critical damping system. Now I am introducing the critical damping characters of rho. It is means of ratio between the critical damping ratio. Rho is critical damping ratio. It is called as C, critical damping to the damping ratio. Damping. The critical damping ratio is the ratio between the actual damping to the critical damping. So, critical damping ratio is the always equal to 1. Is always 1 because C is equal to Cc in critical damping ratio. We are characteristic equations for critical damping is real. Here the equal and real, hence the roots of first roots is alpha, second root is beta. Then equations for the equal and real is x of t is equal to e alpha t within the bracket a plus beta t. It is the equation A. We will apply the value of alpha is c by 2m. Dear students, we already the critical damping ratio is the e power, because the roots are equal and real, hence the equations will be e power minus c by t within the bracket a plus bt. That is the equation number 9. I am taking the minus c by m and c by cc and c by cc. Put into the denominator c by c and numerator c by c. We already know minus c by cc is rho, that is the damping ratio, into cc by m. Cc by 2m. Here I am introducing Cc by Cc and numerator and denominator. C by Cc is the rho, and C by 2m, if we already know that omega n, then the equation 9 will become the e power rho omega n t a plus beta bt is equal to 0. This is solution for the critical damping system. If introducing the critical damping, the slowly decrease to the 0. See, first Tn, T suffix n is natural period, 2 pi omega n natural period. So the definition for the critical damping is the minimum damping is required for the equilibrium condition. Okay, power damping system. Power damping system is greater than 1. This rho is greater than 1. Okay, we are taking minus c by m plus or minus root of c square by m square minus divided on root this is the equation 10. Here roots alpha beta are This is the equations for the equations we are writing the radial form. What I am going to do in equation 10, all the terms multiply by omega n divided by omega n. Then what I am going to, I am removing the minus omega n. Yeah, means I am taking common minus omega n. This term I am writing as common. Also, this also omega n square is n by k by n. If listen, what happened here already 4 is there. If I am taking common denominator means it 4 will come. Again 4 minus 4 divided by 4, it will cancel. So I write like this. This is equation 11. Now C divided by 2m plus or minus. Now what I am doing in 11th equation multiply and divided by what happened? I am multiplied by omega n divided by omega n. Hence it is roots. So I am multiply and divided by omega n square. What I am doing that commonly I am taking minus omega n. The equations 11 is this one. What I am doing commonly since omega n is n square is root out by k by m, so m by m it will become 1. This is denominator is 4. Then I am taking commonly this one 2 m omega n square. The equation become the c divided by 2 omega n c square m omega n is equation. The equation will be minus omega n. Here c divided by cc is this value we already obtained from the critical equation. We already know rho is, that is damping ratio. Damping ratio is C by Cc. Then I am going to substitute minus omega n so that Cc value was that root alpha and beta roots is, this is the alpha and beta values is this one. So I am going to apply this one. What is this one? Roots are real and distant. Correct? A is equal to A e power minus rho plus or minus root of rho square minus 1. First one you take plus. Next one b is equal to e power beta. Beta is minus rho minus root of rho square minus 1. This is this one. This is the equation for the overdamping. X of t we can write as the rho omega n a omega n rho square minus 1 beta omega n rho square. We can write like this also. The damping, this is the higher, medium, lower damping. Low. What do you understand? If higher vibration, over damping means the time to air, the duration is more. Suppose it is 1 natural period, 2 natural period, 3, 4. You take more time to decay the vibration. Similarly, the medium it will take 3 natural period, but low vibration it will take lesser time. That is if the overdamping if overdamping system, the higher value to decay, more time to initial conditions. It means if higher means decay means initial conditions, reduce the vibration, more time required. Similarly, lower vibration take lesser. The equation for the untapped system, we already assumed it is less than 1. So, the tapping ratio is less than 1. We are taking from the overtapping system equation alpha 1 and beta 1 is equal to minus omega n and this is the equations for this. That means if I need untapped system is less than 1, so I am taking minus 1 from this equation, then it will become the omega n, it will rho plus or minus what I am doing, this is equation for the overtapping system. In overtapping system, I am taking this minus 1. If minus 1 I am taking means this minus plus. Here I am taking inside the root I am taking minus 1 means it is imaginary number minus root of I root of 1 minus rho square. This is the equation 13. Equations for the untapped system is what we already assumed in the previous. It is imaginary and complex manner. So it is complex because I is imaginary number, also complex manner. So x of t is e minus rho omega e power I. Here what I am going to introduce omega d, it is tapping, it is omega d is omega n root of frequency, omega n is natural frequency, omega d is damping frequency. Damping frequency. So what I understand, I am omega d damping frequency occurred in the underdamping system, omega n root of 1 minus rho square. I am rewrite this one. This is the pattern for the vibration. You see, after decay again it will increase and again. This is peak displacement. It is called as amplitude. That is T is 2 by omega n. So, dear students, in this class we concluded derive the equations for the free vibrations with damping. The three types of equations derived from the damped frequency. One is over damped, another one is under damping, another one is critical damping. From the critical damping, the radial functions, we are taking the basic terms and substitute, we find out the over damping equations and critical damping system. Thank you. Next class we see the free vibrations without damping, forced vibrations. Okay, thank you.